Hello guys, welcome back to learning microcontrollers. In this video, I'm gonna show you how we can blink an LED using timers of PIC18F452 microcontroller. So let's get started. So guys, this is our PIC18F452 microcontroller having 40 pins. It's a DIP variant. I'm gonna use PIC18F4620 can also be used. They both have nearly the same configuration and same specs. So whichever you use depends upon you. So guys, let's get started. I am only gonna use an LED 5mm LED to demonstrate to you the blinking using timer. And for this LED, as you can see, it has two pins, one longer, one shorter. The longer one is the power pin, the shorter one is a ground pin. You cannot shuffle these two pins, they must remain the same. Now to interface this with a PIC, we need a 220 ohm resistor. So I'm gonna use this resistor. Now let me show you how to connect it. You connect one end of the resistor directly with the power pin of the LED, and the other end of the resistor will go to any available digital input output pin of your microcontroller. For that purpose, I'm going to use a pin number B0, that is port B, pin 0. Now for the ground pin, directly send it to the ground of your PIC microcontroller. So this is our hardware. So let's get to our MikroC coding and Proteus simulation. So let me first get to the Proteus. In the Proteus, let me zoom in. Okay, here we have zoom. So first of all, you open a new project. Okay, this is a new project. Click on IS. Here, no matter whatever version of the Proteus you are using, this will remain the same. So go to devices, select the components, write down PIC18F452. This is PIC18F452. Place it on the screen somewhere. Go back, take an LED, whatever LED you prefer. I'm gonna use a 5mm black LED or blue LED. Okay, this is the blue LED. So place it anywhere you prefer. I place it here. Now we need a 220 ohm resistor. In the simulation, it is not necessary, but in case of actual hardware, you will need a resistor to limit the current. Now connect them. It goes here, here, and then we ground the LED. Use the virtual ground like this, and you click on here to ground it. Now for the MCLR, click here on the terminal. There is a power. Place it anywhere on the screen you prefer, and then send it to the MCLR pin. Now the crystal we are going to use is a 20 megahertz, like this. Now let's get to the MikroC for PIC. So we can start coding. Let me zoom out. So this is our MikroC for PIC. I'm going to use a version 5.6.1. You can use a higher versions, but they have some differences which you can cater for by simply changing the small letters to capital, selecting libraries, etc. But I will suggest you use the same version I'm using. Learning Micro 1, and I am using PIC18F452. Crystal I am using is 20 megahertz. I click on next, 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 and finish. Now first of all, declare an output pin, that is tris b.f0 equals to 0. That port B, that is pin number B0, becomes an output pin, and initial state of the pin must be 0. That is, the LED at initially must be off. Also place it above it in case of an error. Now start the forever loop, write while one, and then in the forever loop you have to first turn on the LED. That LED turns on whenever the code starts. It means LED is on. Now LED should be on for I say like 0.5 second. For 0.5 second delay, we usually write this command, delay ms500, like this. Now to turn it off, I'm gonna again place it here like this. It is like blinking an LED. This is a normal way of toggling an LED for 0.5 seconds. Let me show you on the Proteus. How does it works? Let's get to the Proteus in our simulation. Double click. Now select the code we just created. Go to the location where you have saved the code. This is the code. Now I run the simulation and show you. Okay, the LED is blinking as shown, as expected. Also change it to 0.22K. In the simulation, this resistor and its value doesn't matter, but in case of actual hardware, you need a 220 ohm resistor, as your LED may burn. See, it is blinking for 0.5 seconds. But the problem with the delay is that it is not a patterned way of using, you can say, timers. It is not a patterned way. It can have errors in case of complex applications. So to cater for this, the proper way is to use a timer. Now we remove this and we use a timer here instead. For that purpose, we initialize a timer known as TOCON timer 0. Timer 0 in the case of PIC18F452 is 16-bit. Like this, go to the data sheet of PIC18F452. Here you can see that here, take a look. Now timer, it has 1, 2, 3, 4 timers. You can use any timer as you like. There are 4 timers, and each timer has some feature. Like timer 0 can be used in 8 or 16-bit mode, but we are going to use it in 16-bit mode. It can use as a timer or counter. Timer 1 is a 16-bit, timer 2 is a 8-bit, timer 3 is a 16-bit. We are going with the timer 0 in this video and in 16-bit mode. For that, let's do the coding. So TOCON equals to 0 cross 07. Now see 07. Now go to the quick converter. This is hex. In hex, 07 means sending 3 ones. Now go back to the datasheet. Let me show you. I am setting a prescaler to 256. So for that we need to go to the page called timers. Okay, there it is in the library. You have here timer 0 module. Click on it. Now see, this is our timer control register. You can see that it has 8 bits. This is TOCON. I am setting 111 to these 3 points like this. That is PSO0, PS1 and PS2. These means prescalers. So in the chart, if you go down here, you can see that if we send 3 ones, it means the prescaler value is 256. So now I go back. See, I am sending 111 to this prescaler. So it means the prescaler I had set is 1:256. That is the highest value I can set. Now our prescaler is set. We can go start. You can say programming the timer register. Now first of all, TOCON, that is a timer control register, T0 con, that is timer control on. TO timer 0 control on bit, TM or 0 timer 0 on equals to 1. This commands enables the timer 0 enabled. See, if you want to confirm this in the datasheet, you can go back to this page on the datasheet. Here you can see that this is timer 0 on, the first one, this. Now here you can see timer 0 on of control bit enables the timer 0. So I had just enabled the timer 0. Now I go back. This is the first command. Then timer 0 H, because it's a 16-bit timer, so it has 2 bytes, high byte and the low byte. So this is the high byte we are going to give. I will tell you how to calculate it. Timer 0 L or L equals to whatever the data you are sending, like the delay you will calculate will be entered here. One will be the high byte, one will be the low byte in case of a 16-bit timer. In case of a 8-bit timer, you only need to give timer 0 only 1 byte. But for 16-bit, you have 4 bytes, 2 bytes like this. F, 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 F. You can call that first 2 F equals to high byte and second 2 F equals to low byte. So this is what we calculate. Let me show you how to calculate this timer high byte and the low byte for any time. Now let me show you how to do this. So Now take a look here. First of all, the crystal we are using, we must know the crystal. I am using the crystal oscillator of 20 megahertz. And then the next thing is, what is the CPU frequency? CPU frequency, that is divided by 4. It is the internal architecture. Whatever the crystal you select, you must divide it by 4. If it is 16 divided by 4, it will be 4 megahertz here. So this is internal architecture, it cannot be changed. This can be changed. You can remove or attach another crystal, or you can use internal crystal depending upon your requirements. Now the prescaler I said, as already I had shown, I had selected 1:256. And now the F timer, what is the timer frequency? It is F CPU divided by prescaler. You have to divide prescaler by the CPU. So it will be 5 divided by 256, 19531.25. In case you change this crystal, then you have to redo these calculations. Now for the timer T, this is timer T for one cycle. See, this is the time for one cycle only, that is 1 divided by 19531. We get for the one cycle or one count, it will be 51.2 microsecond. So now the next thing is, for this is for one cycle. Now if we want to get the time for hour count, like we want for 0.5 second, then you divide the 0.5 divided by this one cycle time, 51.2 microsecond. You divide by this and you get this 9765.625. In case any other time you want to generate, you only have to change this with this crystal setting. If you have a different crystal, you have to change the crystal first, this, and then you have to change this time. This is in case of this crystal, you can generate any time, you only have to change here. Now the next thing is, timer 0 is in 16-bit mode. So 2 power 16 is 65536. Now what we have to do is that we have to subtract this value, the value we get from dividing the time by the cycle, one cycle, our time divided by one cycle. So we get this value 55770. Now this is in decimal form, we convert it in a hex form. Now this is our high byte and this is the low byte. That is what we have to enter in our coding. So let's get back to our coding. Now in the coding you can see that he was asking for the high byte and the low byte. Now the high byte, as I had shown you there, is calculated to be D9 and the low byte is calculated to be DA, like this. Now this is our high byte and this is the low byte, and it is in hex form, 0 cross D9, 0 cross DA. You can enter it in the decimal form as well, or binary form, doesn't matter, but I am using the hex form. Now this will be a delay of 0.5 second. If you want to change the delay, you only change this. Now our delay has, timer has started. If you leave the code here, it will remain on, but we have to do the toggling. For that purpose, we have to switch off the timer as well, that it should now turn off. For that purpose, we use an interrupt, while intcon dot timer 0 if double equals to 0. Now intcon, that is the interrupt control register, will register timer 0 if that the timer interrupt is 0 now. If it is 0, then tocon, that is timer 0 control register, timer 0 on equals to 0 now. Now here you can see that we turned this on. Now we turn this off. See, we simply make it 0. It was 1 when the timer started. LED is turned on and timer has started, and this delay has been generated by the timer, and now we have to turn it off, and it has given an off pulse that the timer has done the counting. Now this is a unique feature of PIC microcontrollers, that many PIC microcontrollers do have the interrupt overflow flag. Now it has overflown to be 0. So now we do is that timer intcon, that is the interrupt control register, timer 0 if equals to 0. Now what we did here is that our timer 0 con, now interrupt control register, timer 0 if it has become 0. Now we had cleared the register for next generation. If there is already a value, then this while condition for the next delay will cause trouble. So that's why we have cleared it manually. Here we got the 0 and now we are out of the loop, and now we cleared the register because we got our required reading. Now we copy this whole This is now you can say a delay of, you can make a function out of it, delay of 500 milliseconds using timer, starts and it ends here, ends. Now you can use it instead of the delays. You can remove the delay commands and you can place them there. It is exactly the same, that is 0.5 second. Now I build the code and go back to the Proteus, and we again run the simulation with the new code. See, it is doing exactly the same, now this time with a timer. You can see that in this way, guys, you can generate delays using timer, and this is the most patent way of generating a delay, because in case of a delay command you only are using the loop statements in the assembly line, which is not a good thing. In case of long delays and other stuff, and after a long period of time, if your microcontroller is installed in an industrial environment or somewhere, it will start to lose the timing control, because loop is not a patent way of doing the job. So this is the proper way. So guys, I hope you learned something from this video. Thank you very much for your time and have a nice day.